In this problem, we are tasked with finding if a integer we are given is a palindrome. So here's two simple examples to explain the problem. This number right here is a palindrome. A palindrome means that it's symmetric. We can fold it on itself and it's going to be equivalent sides. So this goes 1, 2 from that side, and then this goes 1, 2 from that side. So this is a palindrome. But if we have a negative number, it's not a palindrome. The obvious thing we could do is we could just turn these integers into strings, which we could use a library function in an interview. I mean, the point of the problem is so you don't do that and you find a way around to actually manipulate on the actual integer. And we wouldn't want to do that. Turn it into a string, linear time, and we wouldn't want to go that route. Either way, it will be linear time because we have to examine each digit. One way we can do this is operate on the actual integers. If we see that it's negative, it would just automatically not be a palindrome. And then we could chop off each character and then check them. Is 1 equal to 1? Yes. And then we go inwards. We'd have to actually manipulate the exact integer. This problem isn't really a test of thinking, it's more of a test of whether you know how to manipulate integers. We're going to look at that. So we can jump right into the code so we can get an exact look at really important subroutines I want to show you that you need to understand to manipulate integers and chop off values because you need to check them. So let's look at the code. Let's take the example of 9,239. That is not a palindrome, but we're gonna see how we can break that down. So first off, we check if the number is negative. It's negative, it can't be a palindrome. And then we're going to take the logarithm of this answer. Why do we take the logarithm? Remember what the logarithm is. It's a question. We're gonna take the log base 10. Normally we deal with log base 2s, but it's 10 in this case because we want to know how many times do we multiply 10 by to get the length of this number. And why do we do this? We want to know the amount of digits. If we know the amount of digits, that's very helpful because we need to generate a mask later to chop off items. And you'll see what I mean by a mask. 10 to the what equals 9239. The answer is about 397. 10 to the 3.97 is going to approximately equal 9239. What does that tell us? That tells us how many digits there are because what we will take is the floor. The floor just means chop off the decimal place. And then we're left with 3. And more exactly, the floor finds the closest integer that is less than the decimal or integer value, 3.97. The closest integer that's less than 3.97 is 3. That's the floor of it. It just chops the decimal place off. And now we would add 1. So that gives us the amount of digits, which is 4. So this is just something you need to know. Why a logarithm? We want to see how many times do we multiply 10 times 10 times 10 to approximate to this number. We take the floor of that and then add 1 to get the number of digits in the number. So it becomes this, and this is the code. Now we have the total amount of numbers in this integer, which is 4 digits. What we can do is we can generate a mask. Why do we need a mask? So we're going to desire a mask of 1,000, which would look like this. And why do we want a mask of 1,000? Notice there are 3 zeros. 1,000 is 10 to the third, which is 10 times 10 times 10. We're just tacking on a bunch of zeros. Why do we need this mask? The mask is going to allow us to chop off the final digit. If we do 9,239 divided by 1,000, we get this. That value is either a float or a double. If we store that as an integer, it will truncate the decimal place, and it'll just become 9. By chopping off the decimal place, we're effectively saying, forget about the remainder. How many exact amount of times can this value go into 1,000? It's 9. And what does that do? It chops off the 1,000th place. And it says, forget about 239. That's not fitting into 1,000, it's remainder. So it just chops off the 1,000th place. That's what our mask will do. It'll help us get the first item. And that's the whole process we're doing now. And then the final item can be chopped off by just dividing by 10. If I divide that by 10, what happens? We get 923. If we chop off the decimal place by representing this as an integer, because that's what happens when you convert from a double or float into an integer, it's a conversion where you will lose data if it has a decimal place, because integers don't have anything past a decimal. So this would become 923. What happened? We chopped off the last guy. And that's exactly what we need. If we can chop off the first guy and the last guy, we can compare them. And then we advance, we update our mask, and that's the whole fundamental of this problem. It's just a matter if you can do the math and you understand logarithms and how to generate this stuff and deal with primitives. Next, we're going to generate the mask. We generated the mask. How many zeros are in it? there's going to be 3 zeros because we want 1,000. We do 10 to the total digits minus 1, which is 4 minus 1, which is 3 in this case. So we generated the mask, which is 1,000. And now we just iterate. We iterate from the left to the right, and we're going to iterate only until we get to the half, and we're going to compare. Guys at the ends, 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 and then once we're at the middle, or if this is an odd number, we're going to reach the middle. If it's even, we're going to have 2 items and then cross ways. We end the iteration. So we make a for loop for that. We're going to do a for loop from I equals 0 to the amount of digits divided by 2. So if I have 4 digits, I'm going to go from 0, 1, and then I wouldn't hit up against the 2 because if I have 4, that's 4 divided by 2, 2. It would only go to half. If I had odd, for example, if we had length 5, we'd divide that by 2, get 2.5, and then again, we'd only go up to index 2. So we wouldn't touch that guy right in the middle. We're just going to say 0, 1, not touch the guy in the middle. So here, let me draw a picture. This guy is even, length 4. That guy is odd, length 5. 4 divided by 2 is 2. 5 divided by 2 is 2.5. Truncate the 0.5 because this is an integer. And then that becomes 2. So either way, we're only going to go up to the 2. It's a less than sign, so we don't touch 2. We're going to stay 1 behind it. So 0, 1, 0, 1. In the even case, fold over. We compare everything we need. In the odd case, fold over. We compare everything we need. Guy in the middle does not matter because he can be whatever he wants because palindromes only care about the edges, and then if the middle guy's just sitting alone, he's sitting alone. So that's the exact indexing. So next, we're going to extract the guy at the end, extract the guy at the start. So why did we use the mod operator? Let's go back to our example. The mod operator says, what is the remainder if I divide by 10? If I divide by 10, I get 923.9. And that 9 right there, the 0.9 says, hey, we had a remainder. That remainder is 9 itself. So when we do mod, we say, what is the remainder of dividing by 10? It's going to be 9. And that is the way you extract the ones place. That's how you extract the farthest right digit, and which is in this case is the least significant digit. And that's what we do here. We do the same thing, and we also use the mask to get the most significant. And then we just compare these values with a Boolean operation. So this is the bread and butter of what we're doing. We're extracting the 2 sides, comparing them. Our for loop enforces we're only going to go as far as we need in extraction and comparison. We need to adjust the mask. So we say x mod the mask. Because remember, if we do the remainder, we're saying, if I do division by this value, 9239 divided by the mask of 1,000, we're going to get 9.239. What's the remainder? It's that decimal, 0.239. And then that decimal is 239, so we chopped off that 9 at the end. The mod gets us everything behind the decimal, division gets us everything in front of the decimal. And we can do that here. Then we need to chop off the guy on the far end. And how do we do that? We use division. If I divide by 10, I get 923.9. And if we store that as an integer, that effectively destroys the decimal place. So we get 923. We remove that final part. But in reality, we actually already removed the first part. So we had removed the first guy. And then if we divide that by 10, we get 23.9. And then if it's an integer, it truncates the decimal. So that's basically all we're doing. Finally, we need to adjust the mask, as you can see. We can't do anything with that because we need to fix it so that we can extract the biggest guy again. And what do? We divide it by 100. The reason is we just removed 2 guys. We removed 2 digits. So our mask needs to lose 2 zeros so it matches up again. So let's divide the mask by 100. And then finally, if everything goes right, we will reach the bottom and return true. So every for loop's going to do exactly what we just said. Comparing them, if something goes wrong, return false. If everything's fine, we come down here and return true. So for the time complexity, we're going to be iterating half of the digit in both cases. Roughly, in the odd case, it's roughly half, because it's hard to split an odd number. That means we're going to be doing linear time because everything looks constant here. These are all constant time operations, all arithmetic operations. That's linear for the time complexity. And then for the space complexity, we're storing nothing in terms of auxiliary space. If the number gets extremely large, our space storage will not scale with the input asymptotically. That is the time and space complexities, linear and constant in space. It's a fairly straightforward problem, but we saw that if we want to get the decimal place, we use mod. That's something that's going to be useful. Mod is also useful for wraparounds. If we want to wrap around an array, we're going to see that in other problems like implementing circular structures that live within an array, but we need to wrap around to the beginning of the array, like a circular queue, as we'll see. We also have division. Division allows us to chop off the decimal place by whatever we divide by, because everything to the right of that decimal will disappear. So mod gets us what is in that decimal, division gets us what's not in that decimal, and that allows us to operate on integers. So that's something that's good to know, and that's one thing you can take away from this problem.